Yeah, good morning, students. So in the last class, we discussed about some concepts based on this dielectrics and some problems related to the dielectrics. And see the some more concepts based on the dielectric, and later we discuss some problems, remaining problems based on this dielectric here. So this is one of the important concept based on this is force acting on the dielectric slab. So in the last class, we discussed some of the problems based on the work done in placing the dielectric in between the plates of capacitor, or work done required to remove the dielectric placed in the capacitors, right? So there I said there will be some attractive force between the dielectric and that capacitor, or the plates of the capacitor. So the reason there, that is nothing but because of this induced charges here. Suppose here I am assuming like this is a positive charged plate and this is a negative charged plate of this capacitor here. So just we are introducing a part of this dielectric here, so that some part is there inside. And so then what will happen is we know some sorry, some negative charge will be induced near this positively charged plate, and this side opposite charge like positive charge will be induced here. And so now there will be some attractive force between these two charges, and there will be some attractive force between these two charges. And so that the net force acting on this dielectric will be along this direction here. So just once you introduce this dielectric and release it, then automatically it enters into this dielectric there. That means into the capacitor there. So there will be, just whenever you are introducing the dielectric in between the plates, so there will be some attractive force will be there. That means the capacitor itself will pulls the dielectric into that plates there. That means inside this capacitor. So that is the attractive force here. Now we need to derive that how much force is acting on this dielectric here. So for that, what we are taking here is, we are assuming a dielectric of the dimensions which are same as that of the dimensions of the plates. That means area of each plate I am taking as L into B, and the separation between these plates is D I am taking here. So let us assume that capacitor completely fills the space between the plates there, right? And so that here then just we are writing the capacitance of the system here. So until this we are taking it as C1 where there is no dielectric, and then here this we are taking it as C2. And so now I am writing the expression for this C1 and C2 here, capacitance of that means we are going to calculate the effective capacitance first. So that effective capacitance means capacitance of this part, you can write it as epsilon naught L minus X, this length, into this dimension will be B. For that plate, this dimension is L we are taking here, and so this dimension width will be B you will get here. So right, that is L minus X into B by D, right? And so then for this capacitance we need to write it as it is filled with a dielectric of dielectric constant K. Suppose this dielectric constant of this dielectric is K here. So K epsilon naught into X into B. This length is X, and again this dimension is B, perpendicular to this plane. And so then effective capacitance means, we know when dielectric is filled like this, we solved in the previous classes many problems, we need to write C1 plus C2. This C1 and C2 both are in parallel. So we need to write that as C1 plus C2. Then you will get effective capacitance like this, right? Then we need to discuss about the force acting on this dielectric. So first mention that about that, write the initial information related to that. When a dielectric is introduced between the plates of a capacitor, when a dielectric is introduced between the plates of a capacitor, the opposite charges will be induced on the dielectric, and so that there will be some net attractive force acting on the dielectric as shown. Net attractive force acting on the dielectric as shown. Consider a parallel plate capacitor having area of each plate as L into B and separation between the plates as D. It is connected to a cell of EMF V. It is connected to a cell of EMF V. A dielectric of dielectric constant K is placed into the capacitor such that X is the length of the capacitor X is the length of the dielectric inside the capacitor as shown. X is the length of the dielectric inside the capacitor, placed inside the capacitor as shown. So then and then you may note this C1 and C2 effective capacitance. Now see this, here there are two cases are there here in that force acting on the dielectric. Like we discussed the force between the two plates of the dielectric. So in that also two cases we discussed there. When battery is continued in the circuit, that means potential difference remains constant and a charge remains constant, right? And so here similarly here also the force acting on the dielectric also two cases will be there. The same two cases when potential difference remains constant, and the second case is here when charge remains constant. So first let us see when the potential difference remains constant here. So when the potential difference remains constant, generally this force means we use that force and potential energy relation, and in both the cases, and from that we derive the force expression easily. So now when the potential difference remains constant, we know the energy can be written as half CV square formula. So here C effective into V square we are writing. And so now we know this energy, that force and potential energy relation is F is equal to minus du by dx. Just we are using that equation to calculate the force acting on this dielectric here. So it is minus d by dx of half C effective into V square, and we are substituting this C effective from this equation here. So that you will get this constant terms I am writing here, only this is the variable terms here, L minus x and plus kx, so that I am writing here. And if you differentiate this, then L differentiation is 0, x differentiation that is 1, that means minus 1 you will get 0 minus 1, and here x differentiation is again 1, so you will get k. And so finally we are writing the magnitude of the force acting on this dielectric here. So that magnitude of the force acting on the dielectric is nothing but epsilon naught bv square by 2d into k minus 1. So that is the magnitude of the attractive force acting on the dielectric when the potential difference remains constant. And so the important thing here is you can observe that this expression is independent of x. So independent of x means how much length it is there inside this. So that means when potential difference remains constant, when the potential difference across the capacitor remains constant, the force acting on the dielectric does not depend on the length of the dielectric inside the capacitor. So mention that clearly here. Just I mentioned this force is independent of x. So mention what is that x clearly. When potential difference constant, this is the only case. That means that when this, in this case it is independent of x. When potential difference remains constant, the force acting on the dielectric is independent of length of the dielectric inside the capacitor. Length of the dielectric inside the capacitor. Right? So that is when potential difference remains constant. And similarly, in a similar way, let us see when force remains constant here. So now we can say this, when force remains constant, I can write this energy is equal to q square by 2c you can write. So that's what I am writing here. So U is equal to q square by 2c. So when charge remains constant, then q value will be a constant value. We are assuming that like capacitor is isolated. Isolated means there is no chance for the flow of charge from that capacitor to anywhere, and so that the charge on the capacitor will remain constant. And so then again the same relation, potential energy and force relation we are taking, so that that force F is equal to minus du by dx, and that value we can write as q square by 2. I am writing outside d by dx of 1 by C effective, right? Now again that C effective value we need to substitute that. So it is 1 by C effective we need to write here. So I am writing this constant terms outside. So 1 by C effective means then d by epsilon naught b you will get here, and d by dx of this value. And so here just what I am taking is x term common I am taking there. So then L plus x I am taking common, then k minus 1 you will get. So this is the L plus x minus x of k minus 1. And just we need to differentiate this, and you know the differentiation of this. The like 1 minus ax plus b form is there. So then it is minus 1 by L plus x into k minus 1 whole square into k minus 1 internal differentiation. This value coefficient you will get there, k minus 1. And so then finally this is the expression for this force here. So the q square into d into k minus 1 by 2 epsilon naught b into L plus x into k minus 1 whole square. So that is the force acting on the dielectric when charge remains constant. So now here you can observe that when charge remains constant, it depends on this x value here. So here x is there. So that means now in this case it depends on how much length is there inside that capacitor there, right? So note that after this expression mention that. Therefore, when charge remains constant, the force acting on the dielectric depends on length of the dielectric placed inside the capacitor. Right? So let us see some few problems based on this. So you need to identify that whenever this force related questions are there, you need to identify whether the potential difference remains constant or the charge remains constant. So that means depending on that, we need to change the expressions there, right? So that means in this case you will get one expression, and in this case when charge remains constant you will get another expressions there. So that means you need to identify which remains constant. Then let us see a few problems based on this. Now write a problem based on this force acting on the dielectric here. So write down this problem. That means the dimensions, a parallel plate capacitor, write down the data. A parallel plate capacitor having plate area A and separation between the plates D. Is connected to a cell of EMF V. A dielectric of dielectric constant K is released from rest by placing a length x naught in between the plates as shown in figure. Then find time period of oscillation of the dielectric. By assuming friction is negligible. Friction between plates and dielectric is negligible. Or you may consider neglect any type of dissipative forces there. It means by here actually I am saying friction between plates and the dielectric, we are neglecting that. Right? So just we are taking it as an oscillatory motion, and we need to derive an expression for this time period of oscillatory motion. Now see this, the force acting on the dielectric. So here the case is the battery remains connected in this capacitor here, connected to the capacitor. So that is our case. Potential difference across the capacitor remains constant. And the area of the plate is given. So I am taking the dimensions as L into B. So finally you may replace that A is equal to L into B, you may write that. Right now our case here is, as we discussed in the previous discussion, like two cases are there. So one case is potential difference remains constant. So that is a given case here. So potential difference remains constant, so that I am taking that formula here. When potential difference remains constant, we just derived an expression for this force acting on the dielectric. So F is equal to epsilon naught B V square by 2D into K minus 1, right? So it is the force, the magnitude of force acting on the dielectric when potential difference remains constant. And there that the mass of the dielectric is also given. So mention that mass of the dielectric in that data. In brackets mention that given M is the mass of the dielectric. So then we are writing the acceleration here. The acceleration of this dielectric is F by M, right? And so then this F value just we are substituting here. So then you will get epsilon naught B into V square by V square into K minus 1 by 2 MD, right? And so the important thing here you need to observe is this acceleration is a constant acceleration. So this acceleration is constant acceleration means you may conclude that the oscillations of this blocker or the oscillations of this dielectric are not SHM. You should be clear that. So it is not SHM, just oscillatory motion, right? Now how it becomes oscillatory motion means, now let us see this. Just I am taking, first let us see here, I am taking the time taken to travel this. That means time taken to completely enter this capacitor I am calculating here. X naught length is there inside initially, so L minus X naught is there outside. So now I am calculating how much, that means this length is nothing but L minus X naught here. Now I am writing this, how much time is required to travel this distance. So that is I am taking it as T1 here. So then S is equal to half a d square formula we are using, that we can use that equation since that acceleration is constant, right? So no need of any SHM principles here. So because the motion of the dielectric is not SHM, that you can conclude from here acceleration is constant acceleration. So you need to use the kinematic equations. So from this we are writing this T is equal to under root of 2 into L minus x by A we are writing. So now here I am concluding that if T1 is the time taken to travel this L minus x, the time period of the oscillation of the block as 4T1 I am directly concluding here. So how it becomes 4T means, now let us come to these diagrams what I mentioned here. So now let us come to these diagrams here. So this is our T is equal to 0 situation. T is equal to 0. This is the situation there. X naught length of the dielectric is there between the plates and remaining L minus X naught is there outside. So now what we calculated T1 is that the time taken to travel is L minus X naught here. The time taken by this dielectric to travel this L minus X naught. If it is traveling L minus X naught, then this dielectric will be completely in between the plates of the capacitor. That is shown here. So now this, from this position to this position, it is taking a time of T1, right? So when it completely fills the dielectric between the two plates, is the dielectric comes to the rest? So absolutely no, because there is no other force acting on this. But once the dielectric is completely in between the plates, the net force acting on the dielectric will become zero due to the capacitor, right? So due to the capacitor, now whatever the expression what we are writing, so that expression is there when some length is outside and when some length is inside. So when this is completely inside here, when this dielectric is completely inside, there is no net attractive force here. The net attractive force will be zero when dielectric is completely filling the space between the two capacitors, and when it is completely inside the capacitor, the force will be zero, right? And so when the force is zero here, but by the inertia it is having some velocity here. That means here it is not at rest, it is having some velocity along this direction because it is an accelerating motion. This body starts accelerating here. With some acceleration it is coming in between the plates here. It is moving with some acceleration. So here acceleration is zero means that we can conclude that actually velocity will be maximum at this instant here. The velocity of the dielectric is maximum at this instant. And so now that velocity, as the velocity is maximum or velocity still velocity is there, the dielectric will continues to move from this position also in the towards left direction. So when it is moving towards the left direction, once it starts coming out of the dielectric, then again there will be force acting on the dielectric like this. There will be some force acting on the dielectric like this here, attractive force. What we derived this expression, that amount of force will be there along the direction. As the force is there in this direction and velocity is there in this direction, the velocity of this dielectric goes on decreasing and it will become zero exactly when it comes out of L minus X naught here. Exactly opposite to this, right? So then again it takes a time of T1 because again it has to come from this position to this position. Again it has to travel a length of L minus X naught only. From this position to this position, that means when it is coming out of the left side of the capacitor by a distance of L minus X naught, it has to travel the distance of L minus X naught only. So then as the acceleration is constant, then it takes the same time T1 here. So that from this position to this position it is T1. So from this position to this position it is 2T1. So T1 is from here to here and from here to here it is 2T1. Then again when it reaches to this position, velocity is zero, but still the force is acting along this direction. Now attractive force will be there here. So because of this attractive force, again it starts moving backwards. That means into the capacitor again. So then again it will travels along this direction, and so again it reaches this position here. That means again it is traveling a length of L minus X naught here. So L minus X naught means it will take another time T1, so that the total time from the beginning will be 3T1. So then again reverse of this case here, it is having velocity along this direction, and that velocity will be actually the maximum velocity here at this instant when it is completely inside. So then here the force is again zero, but velocity is maximum, so the body will continues to move towards right, and so finally it will reaches the state like this. Then again the attractive force will be there this side, and velocity is out of this capacitor, so both are opposite, so velocity goes on decreasing, and finally it comes to the rest in this position. This is nothing but our initial position here, right? X naught will be there inside and L minus X naught will be there outside. So again from this position to this position, the dielectric has to travel a distance of L minus X naught outside this capacitor. and so that again it takes the same time t1 here. So now this is nothing but our initial situation, so that we can conclude that one oscillation is completed, right? It is starting from this position and again reaching this position here. So one oscillation is completed. So now the time taken will be, you can observe that 4t1 here. So that from that we are concluding that the time taken is 4t1, the time period. The time period of oscillation of this block will be 4t1, and just we can substitute this t1 here, and just I am substituting this a value, and so that you will get this expression. And sometimes if b is, that means the dimensions of the plate L and B are given, so here it is over for us, so in terms of b. But as I said, or as I given in this problem, sometimes they will give the area of the plate. So from this area of the plate means, then we need to write this area of the plate as L into B, then B value we can replace here. So then just instead of B you can substitute this A by L, then you will get this expression here. So right, so that is the time period of oscillation. So in this you need to remember that the oscillation, that means the motion of the block is just oscillatory motion but not SHM here. So just it is traveling with the constant acceleration here, right? So it is one of the problem based on this force acting on the dielectric, and it is an important problem. Note this. Next, see this problem here. So note down this problem. A capacitor consists of two fixed semicircular plates, each of radius are separated by a distance d. A dielectric of dielectric constant K is also in the form of semicircular plate, fills the space between them, and it is capable of rotating about an axis passing through the center O. The potential difference applied across this combination is V. The potential difference applied across this combination is E. That means battery is continued in that circuit, or you may mention that a battery of potential difference V is connected. That is the meaning here. Battery continued in that circuit. The dielectric is pulled out through an angle phi as shown in figure, and then released. Find the magnitude of torque acting on the dielectric about an axis through the point O, passing through the point O. So that means now in our previous problems we calculated like the force acting on the dielectric. Now simply in this we need to calculate the torque acting on the dielectric. A similar procedure. So just we are writing this now, effective capacitance we need to write here, so that here this is the dielectric. In the blue color I mentioned that is the dielectric here. So it is slightly come out of this plates here. This red color is the plate here. The other plate will be there behind that. And so now here this side it is coming out here. That means now this is the vacuum here, or air is occupied in this region here. So that means now I am taking the capacitor as two parts. So that means until this it is filled with the air. So that means here this air medium is there here, air or vacuum, and this is the dielectric of dielectric constant K here. So that means I am writing it as a two parts. So now we need to write the effective capacitance like our previous problems. So now effective capacitance means, for that what I am writing is area of the dielectric outside the capacitor. That means this area I am writing here. So this area will be exactly equal to area here without dielectric. So that means now that area we can write as area of that sector, half r square into 5 we can write. And so now with the help of that we can write this capacitance here, right? So that means epsilon naught, no air, no dielectric is there in that area or in that volume. so that we can write this as epsilon naught into A. That A is nothing but area of the dielectric outside, R square phi by 2 by D. So epsilon naught A by D formula, just A means equal to just this value. So that is the capacitance C1. Now C2 we need to write here. This capacitance we need to write here. That again we can write as epsilon naught A by D formula, since the dielectric is filled. So K epsilon naught A by D we need to write. Now A means, how to write this area means the area of the semicircle minus area of this C1 we can write here. So area of the semicircle is here pi r square by 2. Sorry, this is pi r square by 2, and so that we can write it as pi r square by 2 minus this value we can write here, pi r square by 2 minus this pi r square by 2 you can write, and so that here this value is pi minus phi by 2d you will get, right? And so then C1 plus C2 we are writing here, then C1 plus C2 value will get like this. And here you can take that phi common, so in terms of that phi you can express this value as epsilon naught r square by 2d into k into pi minus, I am taking this phi common here, then k minus 1 you can write here, right? So then that is our expression for this C, effective capacitance here. Is it clear? And now energy stored in the capacitor we need to write here. The energy stored in the capacitor you can write this as half CV square, since the V is constant here. Now we know in the previous problems we mentioned the relation between force and potential energy, right? So that is F is equal to minus du by dr or du by dx you can write. Now in a similar way we need to write the relation between torque and potential energy here. So then in a similar way you can replace this as torque is equal to minus du by d phi you can write here, right? So just it is nothing but our work done relation here. So work done and potential energy and work done and force relation here. So you can write this work done in force as F into dr you can write. And whereas the work done in rotatory motion you can write this as tau into d phi you can write here. Here linear displacement, here angular displacement you need to write here. So the small amount of work done is nothing but negative of work done by the conservative force is nothing but negative of change in potential energy. So we replace this value as minus du and minus du. From that you can write these relations here, right? So that is just work done definitions only. So from this we can, you should understand that we can write this torque equation like this, minus du by d phi. And again the du means I am substituting this value, so V is a constant here, so V square I am taking common, and you can substitute this C effective value from this here. If you are substituting that C effective value from this, we can write this expression as V square by 2 into epsilon naught R square by 2D into, now this value, the variable term is this one here, so we need to differentiate this one. So K phi is a constant, and so minus phi you will get 1, so that value is k minus 1 you will get here, the total differentiation of this minus of k minus 1, here already negative sign is there, so minus of minus plus you will get. So that means epsilon naught r square into v square into k minus 1 by 4d you will get. So that is a torque acting on this dielectric when it is slightly turned out of this plates like that, right? So that is again when the potential difference is independent of, you can observe that in the force we derived like that force is independent of the x value, right? So here also similarly you can observe that here the torque is independent of that phi value, how much angle it is outside. So that means it is similar here, that is independent of this position of the dielectric or the angular displacement of the dielectric here, right? So next let us see this problem here. So note down this problem. The plates of a parallel plate capacitor, are placed horizontally such that the lower plate is completely immersed in a liquid of dielectric constant K and a density rho. Liquid of dielectric constant K and density rho. The area of each plate is A. And it is connected to a, and capacitor is connected to a battery. such that it supplies a charge of q to the it supplies a charge q to the positive plate of the battery in steady state. Then find rise in the liquid level. In between the plates of the capacitor. So right. So that is a given question here. Two plates are parallel to each other and those two are horizontal. That means those two plates are placed in horizontal. And just we are immersing this one plate completely into the liquid and other plate, upper plate will remains in air. So that some liquid will be there in between the two plates here. So like suppose some level I am taking like this, some level up to this level, suppose this liquid is there here. And so once the charging of the capacitor takes place, then there will be some rise in the liquid level here. So this liquid level will increases, right? That means that increase only in between the plates. Outside the capacitor there is no level, the level will remain same. But in between the plates the level will increase by a small amount here. So now we need to calculate that increase in that liquid level. And you know that liquid level will increase because of the force acting on this dielectric, right? So that means that liquid there will act as a one dielectric there. So there will be some force acting on the dielectric here. So because of that force then liquid will rise here. And so now observe this force calculation here clearly here. Now in this I am assuming that now this is a force diagram I am representing here. So this is a positive plate on the positive charge on the upper plate here, let it be plus q, and the negative charge on this lower plate is minus q. That is the charge supplied by this battery here to that positive and negative plates, right? And so now we know some induced charges will be induced on that liquid here. So that I am taking this as a liquid body here. I am representing just some positive charge here. Actually this liquid is also in contact with that. I will discuss about that. So that here this side some positive charge will be induced on that liquid, and so that I am taking as some q dash here, which is induced charge, or you can call it as a bound charge. And this side, this end of this liquid surface, then here that opposite charge plus q dash will be minus q dash will be induced there, right? So these are the induced charges here. So now let us write an expression for this induced charge or the bound charge. This we discussed already in our first class of this dielectrics. So the induced charge is given by q into 1 minus 1 by k, right? And so now the net charge on the lower plate now we are writing here. So now here we are taking the dielectric medium as a liquid medium, that you need to observe here. So liquid medium means it will be perfectly in contact with that lower plate here. Whereas if you are taking some solid, then there may be a small gap may be there between this solid plate and the dielectric surface there. So but here we are taking liquid, so it will be completely in contact with that lower plate here, because lower plate is completely immersed in that liquid. And so then what will happen is the induced charge on the lower surface of the liquid and the charge on the lower plate will combine with each other, so that some net charge we need to write here. So that now net charge is nothing but I can write it as q dash. Minus q dash is the charge, actual charge on the lower plate, and plus q dash is the charge induced on this lower surface of this dielectric here. So they will combine with each other, so that net charge we can write like this. Just I am substituting this q dash value here, so that this minus q and here plus q will be cancelled. You will get q by k, you will get, right? So that is the net charge on the lower plate. Now I am writing the net electric field in the capacitor I am writing here. So the net electric field in between the plates of capacitor is electric field due to the upper plate and plus electric field due to the lower plate we need to write here. Electric field between the plates means. So electric field due to the upper plate we can write as upper plate is having some charge q, or you can take sigma as the charge density, surface charge density, then sigma by 2 epsilon naught, where sigma is given by q by a, right? And similarly charge on the lower plate is some sigma dash you may consider, for example sigma dash by 2 epsilon naught, and where that sigma is nothing but ql, charge on the lower plate by a, that's a surface charge density on the lower plate. Now just to substitute this q l value here, which is q by a, so I am substituting that value and you can take the terms common. So the net electric field between the plates is nothing but q by 2a epsilon naught into 1 minus 1 by k you will get, right? So it is the net electric field. Now let us come to the equilibrium of this liquid which is rising here. So only this part let us consider here, the liquid which is rising upwards when compared to the level in the beaker. So suppose level in the beaker is up to here. So this amount of liquid is rising. So this amount of liquid is rising means there will be some force acting on this liquid in upward direction. Because of that only it is rising. So that force is nothing but E into Q dash, and the downward force is nothing but weight of that liquid. So weight of that liquid is to be balanced by this electric field force due to this electric field here. This electric field is nothing but this net electric field here. So that net electric field will be there in this direction. That means net electric field will be in downward direction only, but here this is a negative charge here. So force acting on the negative charge is opposite to the electric field. Our net electric field direction will be like this only. But this is the negative charge here. So force acting on this negative charge will be E net into Q dash. It will be opposite to that of electric field we need to write here. So in equilibrium these two gets balanced with each other. It's somewhat similar to that of, we can say, in surface tension when you are calculating the capillary rise. The upward force will be force due to surface tension we mentioned, and the downward force as weight of this liquid column. So because of that surface tension only liquid is rising in that capillary tube, right? And so similarly here, because of this electrostatic force only the liquid is rising here. And so that should be balanced. It will rise until that force is balanced by the weight. So just we need to balance that weight. And weight of this liquid column we can write as mg, and m is nothing but volume of this liquid into density we can write, and volume is nothing but area of cross section into this height we are taking as h here. We are assuming this as h. So then A into h, that gives the volume of the liquid. So A into h into density of the liquid into G we can write, and that is equal to electric field here. Then E dash, E net into Q dash we need to write here, because the Q dash is the charge present on this upper surface of this liquid. And so that Q dash value I am substituting here, like Q into 1 minus 1 by K. And now from this we can write this A value, H value here by writing the remaining terms all side, and finally you will get this. I am taking LCM just here. So Q square into K square minus 1 by 2 K square A square into epsilon naught rho into G. So that is a rise in the liquid level here. So those are some problems based on this force acting on this dielectric here, right? So practice the problems based on this dielectric, and some work done related questions also there. I explained already those work done related problems in our previous class based on the dielectrics, right? So that is about the parallel plate capacitors here. And next we discuss about, there are so many applications of the capacitors are there actually, and those applications we will get in the coming topics here. Like it will be used in many places. That capacitors are used in many places, like in our you can observe that in many electrical devices, whatever the device you are taking, some capacitor will be there in that. So definitely, even if you are taking just a fan, if you are taking for example in your home, then there will be a capacitor in that. So like in many places we use that capacitors, like in circuits in previous, in communications also we will discuss it later. In communications also, like filter circuits will be there. In filter circuits also we use that capacitors, and like modulation and demodulation we will discuss in our communication topics. So there also we discuss, like that means if you want to send the signal from one place to another place, then first we should do the modulation. Modulation means superposition of the message on another signal. And so for that process it is capacitor is required. That means combinations of that capacitor circuits are required. And similarly when the receiver is receiving that, then demodulation is required. So for that also then capacitor circuit is required. Like if you are using a cell phone here, the signal is sent from the telephone, that means your cell phone to another your friend phone. So that means inside your cell, that process will take place. Whatever the information you are talking, that will be superposed into the electromagnetic waves. So that means that finally it will be transmitted as electromagnetic waves, right? When your friend is receiving the whatever the voice you are sending, that your friend is receiving. So he receives the first electromagnetic waves, that is to be separated into the sound waves again. So that means in that process again the capacitors are required. And similarly like the conversion of AC into DC, we use the rectifiers. So in that also some filter circuits are required there. So like that in so many, whatever the electrical circuit you are taking, then there will be definitely there will be role of the capacitor will be there in that circuit, right? In tuner circuits, in later in AC also we'll discuss about that. In tuner circuit, in if you want to tune your radio or television, in the tuner circuits also, if you want to change the frequency in the tuner circuits also, we need to use this capacitors there, right? So like that so many applications are there for the capacitors in our daily life. Whatever the electrical devices what you are using, definitely there will be capacitor in that circuit, right? So then those are the some discussion regarding the parallel plate capacitors. And about the parallel plate we discussed already in our that means like parallel plates will be placed parallel to each other, 2 or 3 plates will be placed parallel to each other, and the charge calculation or the charge flowing through the switch calculations that we discussed already in this Gauss law application. Now let us see some problems based on this parallel plates here. So first write the information here. So 3 identical metal plates are placed parallel to each other and are given the charges as shown in figure. Then write the charge on the each surface of the plate. Then write the charge appearing on the each surface of the plate. So these plate problems we already discussed in the Gauss law applications there, right? There we introduced about this and we discussed what are the basic points are required for this. We discussed already those points there. So like here, when 3 plates were placed or any number of plates were placed parallel to each other, the charges on the main conclusions in the term, the charges on the outermost surfaces are always equal, and that will be equal to the half of the total charge given to the system. So that means now there is a fundamental point here. So we mention that point here. We know the charges appearing on the outermost surfaces will be always equal and is equal to half of the total charge given to the system. Right? So now I am taking like Q1, Q2, Q3, Q4 and so on. And another point what we mentioned there is the charges on the nearest opposite faces are equal and opposite. That means the charge on these 2 faces will be equal and opposite there. So mention that point also. And so first let us write the value for this. That means after that point then you may mention this Q1 is equal to Q6. The charge on outermost surfaces means these faces. So that will be always equal, and that charge will be equal to that of half of the total charge given to the system. Q plus 2Q plus Q by half, that is 2. And so therefore this Q1 is equal to Q6 is equal to, you will get that value as 2Q, right? So that is the total charge given to that half of the total charge given to the system, or which is the charge appearing on the outermost surfaces here. Next, the charges appearing on equal and opposite faces. That means if you know this value, then we can calculate this Q1 value here. So like Q2 value. So but what we can write here is, so that Q is equal to Q1 plus Q2. For the plate A, if I consider here, let us name this as A, B, C. So for this plate A, we can write this relation, and from this we can write this Q2 value here. Therefore that Q2 is equal to, I can write this as Q minus Q1, and therefore this Q2 is equal to Q minus 2Q, which is minus Q. So that means charges appearing on, that means sum of these 2 charges must be always equal to the total charge given to the system, right? And so that just I am taking that here, Q1 plus Q2 must be equal to total charge given to the system. As we already calculated this value, now I am writing this value minus Q. Now mention that the charges on equal and opposite, that means charges on the opposite faces will be always equal and opposite. So mention that point here, that means these 2 are equal and opposite always there. So now Q3, first mention that point. The charges on the nearest faces, that means these 2 faces are always equal and opposite, right? And so therefore Q3 is equal to Q, you can write, that means Q3 is equal to minus Q2 actually. So minus Q2 in the sense Q2 value is minus Q, so that Q3 is equal to Q you will get. If you know the Q3 value, then we can answer the Q4 value. Q4 is nothing but again that will be equal to sum of these two charges must be equal to 2q. Therefore, this q4 is equal to 2q minus q3. So, which is q you will get. If q3 is q, then q5 is nothing but minus q4 we can write here. So, that implies this q5 is equal to minus q you will get here, right. So, that is the total charge given to, that means charges appearing on the different faces here. q1, q6, and this is q2 value is minus q, q3 value is plus q, q4 value is q, and q5 value is minus q. Those are the charges appearing on the different faces. So, the fundamental points here you need to note here is again the charges on the outermost surfaces, this surface and this surface will be always equal, and that will be equal to the half of the total charge given to the system. So, that is nothing but what we are writing here. And the charges on the opposite faces will be equal and opposite. These two charges will be always equal and opposite, right. So, that is from that conclusion you can write the charges on the different faces like this. Now, let us take another example here related to this capacitor now. So, next write down this problem here. A parallel plate capacitor of capacitance C, a parallel plate capacitor of capacitance C is charged to the potential V, is charged to the potential V. Then battery is disconnected, and then battery is disconnected, and a charge Q plus Q is given to the positively charged plate of the capacitor. A charge plus Q is given to the positively charged plate of the capacitor. Then find the potential difference between the two plates of the capacitor. Then find potential difference between the two plates of the capacitor. That means this is a situation here. This capacitor is charged by connecting to a cell, means then you know positive charge will be induced on one face and the negative charge will be induced on other face. And that amount of charge you can write as plus CV and minus CV you can write here, because it is charged to the potential difference V. Now the given information is we are adding a charge Q. We are adding a charge Q to the only positive plate, and so that now the Q will be there here. And so now just we need to apply the same principle here. The charges on the outermost surfaces will be equal to half of the total charge given to the system. Now can you say what is the total charge given to the system here? What is the total charge on the two plates? Only plus Q, right? Because the charge on these two will be positive, equal and opposite, plus CV and minus CV, that will be 0. So that means the net charge on the capacitor, if you add the, once the neutral capacitor is charged, and then if you are adding the, and that means if you are finding the net charge on the two plates of the capacitor, always you will get 0, because positive and negative terminals of the battery will supply the equal and opposite charges to the two plates of the capacitor. That we can consider like that. And so now here, so the only charge on this system of these two plates will be only Q. So that means half of the charge will appear on the outermost surfaces there. So Q by 2 and Q by 2 will appear here, right? That is our principle there. If whatever the charge is there, then half of the charge will appear on the outermost surfaces. So if here if it is Q by 2, then charge on the inner surface of this positively charged plate will be CV plus Q by 2. Already CV is there. Now additionally Q by 2 will coming to the inside. That means simply if you are giving a charge Q to this plate, Q by 2 will appear on the outer surface and Q by 2 will appear on the inner surface. So that the charge on the inner surface will be already existing charge CV plus Q by 2. And similarly the charge on this is negative of CV plus Q by 2. You can observe that net charge on this plate will be only CV you will get. That means inner side is CV minus plus Q by 2 minus of CV plus Q by 2 and outside is plus Q by 2. So the net charge on this negatively charged plate is minus CV1, which is nothing but equal to the initial situation. And so that now the charge on this capacitor means now what is the charge on the capacitor now? We need to take, we discussed already in the beginning or first class of the capacitor, like the charge on the capacitor means the positive charge on the inner side of the positively charged plate. The charge on the inner side of the positively charged plate. So that means now the charge on the inner side of positively charged plate is nothing but CV plus Q by 2. So now you should say the charge on this capacitor is equal to CV plus Q by 2. And so now the potential difference is nothing but that Q by C formula we are writing. Now the charge I am taking just it as Q dash. So that Q dash is nothing but CV plus Q by 2. And so from this you can write the new potential difference as V plus Q by 2C. Right. So that is a new potential difference between the two plates there. Right. And now in capacitors we discussed some switch related problems. like by closing the switch, what is the amount of charge flowing through the switch. Now in this parallel plates also they will ask that such a switch related questions here. And so now that we can, let us take one such an example here. And so now I am taking that the 3 plates are there here. The separation between these 2 plates is D, and separation between these 2 plates is 2D. And now the charge given to this first plate is Q, and next plate is 2Q, and the third plate is neutral. We are not giving any charge to that plate. And so you may name that plates as, for example, A, B, C. So right, just note that problem there. The following figure shows 3 parallel plates. 3 parallel plates placed at the separations as shown. Placed at the separations as shown. That means separation is shown here. It is different. D and 2D. The charges are given to the plate A. The charge given to the plate A is Q, and that given to the plate B is 2Q. C is neutral. What is the charge flowing through the switch after closing it? What is the charge flowing through the switch after closing it? Right? So in switch problems we solved many problems based on the switch here. And so in switch problems, as we discussed previously, just we need to calculate the charge on the capacitors before charge on each plate before closing the switch and after closing the switch, right? So now first I am writing here before closing the switch, what are the charges appearing on the different phases here. So that this is total charge, half of the total charge, the same principle. So half of the total charge is 3Q by 2, and here 3Q by 2 will be there. And so then sum of these 2 charges must be equal to total charge given to the system. And so here it is 3Q, Q minus 3Q by 2 we need to write here. Charge on this inner side of this plate means. So that is minus Q by 2 you will get. If once this charge is minus Q by 2, then this side charge must be equal to plus Q by 2, equal and opposite. And if this is plus Q by 2, as we know this charge already, then this value will be 3Q by 2 you can write. Because sum of these 2 charges must be equal to 2Q. And so then again the equal and opposite charge. So here plus 3Q by 2 is there, and so here then you will get minus Q by 2. And so now we can observe that the plate C is initially neutral. So the initial charge on this plate C is 0 because no charge is given to that plate. So then still it becomes 0. That means minus 3Q by 2 and plus 3Q by 2, right? So now let us close the switch here. Now I am taking the same situation after closing the switch. So after closing the switch means now A and C are connected together. When A and C are connected together, now we can observe that the charges on the outer surfaces will be still, that is equal to the half of the total charge given to the system. So 3Q by 2 and 3Q by 2 you will get. Now the charge on the inner surface is not equal to Q by 2 because some flow may takes place between these plates here A and C because we are connecting A and C. And so that now I am assuming some minus Q is the charge on this, minus Q1 is the charge on the inner side of this A. And so then here it will be plus Q1. Then here the charge is 2Q minus Q1 because sum of these 2 charges must be still equal to 2Q only because B is not connected anywhere. So total charge on B should remain constant. And then this on the C should be equal to, that means equal and opposite. So this is minus of 2Q minus Q1 you will get here. Now simply what we can write here is A and C are connected together. AC, that means A and C are connected together means the potential between exactly same as that of potential difference between B and C because A and C will be at same potential. So just I am using that logic here. That means as they are connected, the potential difference between B and A should be equal to B and C. And here only the important thing is whatever the order you are taking for this, same order you should consider for this also here. Like if you are considering like AB, then this side you should consider CB. Is it clear? Otherwise you will get the different answer, wrong answer you will get. And so that means here BA I am taking, so this side also should take BC. If you are taking for example AB, then this side you should take CB. That order you should consider there, right? So I am taking it as BA and BC. Then potential difference between these two means you can write it in 2 ways now. Q by C we can write as we know the capacitance formula, or you can write it as E into D we can write, which we used in Gauss law because the potential difference will be equal to, in uniform electric field we can write it as E into D, right? So that E value you can consider as sigma by epsilon naught into D you can write. Like that you can write, or you can consider it as Q by A epsilon naught by D. That means Q by C formula you can write. Any one of them you can write, both are equivalent only, both are same only. And so now this side it will be equal to charge on this B will be, so here only important, if you are taking charge on B here, then this side also should take charge on B. If you are taking charge on C here, then this side also should take charge on A, then this side you should take charge on C here. That is important while writing this equation. So on simplifying this, you will get this equation here, Q is equal to 4Q by 4 by 3 into Q. Now I am calculating the net charge on the C. The net charge on C is nothing but this side it is 3Q is there, sorry, this side it is 3Q is there, and this is minus of 2Q minus Q1 is there. So 3Q minus of 2Q minus Q1. This Q1 value I am substituting here, 4Q by 3. So net charge we are getting it as 5 by 6Q, right? And so the initially now we can observe that the initial charge on C is 0. Now finally we are getting some charge here. So finally charge on net charge on C is not equal to 0. And so definitely there must be some charge flowing through the switch only, because it is connected only through the switch here. That is only the path available for the flow of charge. So the whatever the net charge on this capacitor, then that is net charge on the C, that is nothing but I am taking it as charge flowing through the switch S here. Is it clear? Because actually you need to find the difference between initial and final charges. Whereas the initial charge is 0, then directly I am taking it as a final charge itself as a charge flowing through the switch. Or you may calculate the charge on this plate A. Then you can find the difference between initial and final here. Then you will get the same answer. Just you will get the negative sign difference you will get. In switch problems we already discussed that only charge flowing through the switch means you need to answer only magnitude. If they are asking particularly direction, charge flowing from A to C or C to A, if they are asking, then you should mention along with the sign also. Right? Here charge flowing through the switch only magnitude is sufficient here. So it is a way of charge flowing through the switches. And then next in this, some models will be there like connecting to the ground. Sometimes the plates are connected to the ground. So now let us see the problems based on this. So now let us see this problem here when the plates are connecting to the ground. So let us note down that data here. Two plates A and B, two identical metal plates A and B are placed parallel to each other. Are placed parallel to each other as shown in figure. The charge given to the plate A is 100 microcoulombs. The charge given to the plate A is 100 microcoulombs, and the charge given to the plate B is 60 microcoulombs. Then find charges appearing on the each surface Q1, Q2, Q3 and Q4, and a charge flowing through the switch, when, now write the first question in that A, when both the switches S1 and S2 are open, B, when only S1 is closed, and next C, when first S1 is closed and then S2 is closed. First S1 is closed and then S2 is closed. Right? So now let us see the first one here. When both are open. When both are open, then we can answer it easily. Just it is our previous concept only. The charges appearing on the outermost surfaces will be equal to half of the total charge given. So total charge is 160 you will get. So 160 by 2 you will get. So which is 80 microcoulombs here. So this side also 80 microcoulombs. And so then this side it is 80 microcoulombs means then inner side must be equal to 20 microcoulombs here, because the total charge on these two plates must be equal to 100. And then this side it should be minus 20 microcoulombs. Always these two are equal and opposite. Now we can verify that the sum of these two charges will be equal to 60. So that means we can write those Q1, Q2 values directly here. So Q1 is equal to Q4 is equal to 80 microcoulombs, comma this Q2 is equal to 20 microcoulombs, and Q3 is equal to minus 20 microcoulombs you can write here. That is the charges when the switches are open, that is easy. Now let us consider the first case when the switch S1 is closed here. So when S1 is closed here, then we discussed already in the Gauss law applications itself, in the parallel plate combinations, whatever may be the number of plates given here, it may be 2 plates or 3 plates or 4 plates or 100 plates, you may consider parallel to each other. If the fundamental point is, if any one of the plate is connected to the ground, the charge on the outermost surfaces will be equal to 0. So then only it will satisfy that potential difference there. There we mentioned already and we proved already all those conditions there. So just it is a revision of that. You can revise that if you want clear derivations by applying the Gauss law. We already mentioned all those points there in the Gauss law applications. So that means any one of the plate is connected to the ground, the charge appearing on the outermost surfaces, both the outermost surfaces will be 0. That is equal and equal to 0, right? So mention that point here in the case B. In parallel plate combinations, if any one of the plate is connected to the ground, the charge appearing on the outermost surfaces will be 0. The charge appearing on the outermost surfaces will be 0. Right? And actually there we can also mention that charge flowing through that switch will be equal to the total charge given to the system. Charge flowing through the switch is equal to, if only one of the plate is connected to the ground, then charge flowing through the switch will be equal to the total charge given to the system. That means here it is nothing but 100 plus 60, 160 coulombs. You can also answer by after taking this charge distribution here. So that means here I am taking it as 0. And so then here it will be 0 according to the point what we mentioned here. Now still B is this isolated plate only, right? This is our plate A and this is our plate B. Now still B is isolated, that means it is not connected anywhere. So charge on that should be remains constant here. The charge given to this is 60 microcoulombs here. So now this side it is 0 means then the total charge will appear here only. Plus 60 coulombs should appear on the inner side of this plate B. Now if the charge on the inner side of this plate B is 0 means, then charge on the inner side of this plate A must be equal to minus 60, because those two surfaces should carry the equal and opposite charges here. So it is minus 60. And so now initially charge, we need to answer the charge flowing through the switch S1. So now the charge flowing through the switch S1 is nothing but here. You can observe that initially the charge on this plate A is plus 100 microcoulombs. Now it is minus 60 microcoulombs. So how much charge should flow through the switch here? So 160 coulombs of charge should flow through the switch here. That means actually the charge flowing from ground to the plate is minus 160 microcoulombs will flow. So out of that minus 160, 100 coulombs will neutralize the initial positive charge on that plate, and remaining minus 100 coulombs will appear on that plate here. So that means that is nothing but simply they are asking charge flowing to the switch. So then charge flowing to the switch means only magnitude of the charge we can answer here. So which is nothing but plus 100 microcoulombs here. So that is the charge flowing to the switch. So as I said here, if any one of the plate is grounded to the switch, grounded, then if they are asking charge flowing to the switch, simply you can answer that the total charge given to the system will flow to the ground. The total charge given to the system flow to the ground. Whatever it may be 160 coulombs or you may give the 200 coulombs, the charge only will flow through the ground, will flow through the switch here. So it is a charge flowing. You can directly answer like that if any one of the plate is grounded. Then this is the situation here. And so then those are the charges appearing on the different phases, 0 and 0, and this is minus 60 and plus 60 microcoulombs, all those are. And next here I am taking that first S1 is closed, then S2 is closed here. We are closing this S2 also now. So that means we are closing it S2 also means simply you can identify that S1 potential is already 0 because it is grounded. Now S2 potential should also be 0. That means because S2 is also closed here. So that means potential of this plate B should also be 0. Plate A is already 0 and now we are making that plate B also 0. That means there is no any potential difference there. And so if there is no any potential difference means there should not be any charges here, right? The total charge, whatever the charge given to that, whatever the charges initially are there, they should flow to the ground. So the total charge on all the surfaces must be equal to 0 if all plates are connected to the ground. If all plates are connected to the ground, then total charge, whatever the charges present on that plates initially, those charges should flow to the ground, flow to the switch, and so that final charges on them should be 0. So 0, 0, 0, 0, so that there is any potential difference between these plates here. So that means all the charges will be equal to 0. Now charge flowing through this S1 means initially before closing this 60 coulombs or minus 60 coulombs is there, so then means 60 coulombs will be there. That means now plus 60 coulombs will flow from a ground to the plate here, so that it will neutralize the charge. And so then charge flowing through this S2 is also 60 here, because initially plus 60 is there, now it is becoming 0. Then minus 60 coulombs will, microcoulombs will flow from ground to this plate B here, right? So it is the charges appearing on the different plates here. So it means regarding this grounding points, you need to remember that whenever a plate is grounded, the charges appearing on the outermost surfaces will be 0. From that you can answer the charges on the different surfaces you can write here, even though if more than 2 plates are there. And charge flowing to that switch will be equal to the total charge given to the system, or after taking the charge distribution like this, you can answer this. You can answer how much charge is initially there on that plate and how much charge finally there on that plate, right? So that means that is about the parallel plate combination, some problems. We already discussed some problems in Gauss law applications. You may revise those problems also there based on that. So we'll get the more clarity about that parallel plate combinations, right? So that is about totally parallel plate capacitors here. So next, that spherical capacitor and cylindrical capacitors are there. I will explain those about spherical and cylindrical capacitors in our next class, right? Thank you.